today we will discuss about types of electromagnetic induction. So there are two types of electromagnetic induction. First we can say the self-induction and another is your mutual induction. So now one by one we will discuss both of them. First we would like to discuss about the self-induction. So we can explain the self-induction like this. Suppose we are having a current carrying circuit, or we can say if we are having a loop. Let for example this is any loop, and in this loop if I is the current is flowing. So if current is flowing in this loop, so because of the current there is a magnetic field, and that magnetic field lines, if we are looking here, see in this loop current is here in the clockwise direction. So if we are looking the direction of magnetic field, so what we observe by using right hand palm rule or thumb rule, we can say inside the loop magnetic field your inward and outside it will be your outward. So what we observe, due to the current in this loop, there is a magnetic field through this loop itself. So because of this magnetic field, there is a flux in this loop, and that flux we call as a self flux, because this flux is because of their own current or because of their self current. That flux can be said as a self flux. So what we observe, if we are changing the current, or if current in this loop here changes, so self flux will also changes because magnetic field changes. So when self flux changes, so change in flux produces EMF according to Faraday's law. So that change in flux will produce the EMF. So that EMF can be said as a self-induced EMF. So what we can say, the phenomena of self-induced EMF due to change in self-current is called self-induction. So we can write likewise, if a current carrying loop is present, if a current carrying loop is present, so due to own current in the loop, there is a flux associated with that loop, so that flux can be said as a self flux. That flux is called self flux. Just like here, I is the current, so due to that current B is magnetic field, and due to this field there is a flux associated with this loop. So that flux is called as a self flux. So if current in the loop changes, then self flux associated with the loop with the loop also changes. Self flux associated with the loop also changes, and that change in self flux produces induced EMF in the loop, induced EMF in the loop. This is the main point here. So we can say, so the phenomena of self-induced EMF, due to change in self current, is called self-induction. So phenomena of self-induced EMF due to change in self current is called self-induction. Now, so we can say, if I is the current in the loop, then self flux phi is proportional to current I, and that proportionality constant we can write as L. So L is nothing your phi by I. So L can be said, so L is proportionality constant known as coefficient of self-induction. Or inductance. So L is the coefficient of self-induction or inductance. Similarly, if we want to define in another way, we can say phi is your changes as I changes, or we can say, or rate of change of self flux is directly proportional to rate of change of self current. We can say d phi by dt is proportional to rate of change of current di by dt. So d phi by dt is equal to your proportional to di by dt. Then we can write here d phi by dt is equal to your L di by dt. Then further we can write here L is equal to here d phi by dt by di by dt, or we can say here L is equal to minus of E di by dt. So where minus of E means that E is nothing, it is your self-induced EMF. So we can define the L value either induced EMF or self EMF in the loop by rate of change of current, or we can define L or self inductance is the ratio of phi by I. So calculation we can get the value of L by this method. So now see the some point related to inductance or self induction. See, as we have found L is equal to your phi by I, or L can be defined as d phi by dt by di by dt, or we can write modulus of minus e di by dt. So some point related to L we can write. The first point, L is coefficient of self-inductance. Coefficient of self-inductance is a scalar physical quantity with SI unit your Weber per ampere, or it can be written as your Henry also. So first point we can write coefficient of self-inductance L is scalar physical quantity with SI unit is Weber per ampere, or it is also written as Henry. Normally we are defining with a capital H, and its dimension can be defined like this, and its dimension is, see, dimension of L is dimension of flux by dimension of current. And how we are calculating the flux? Flux, as we have found, magnetic flux written as B dot S, S is the area, by current. Further, magnetic field we can define in a simplified form, force by current element into area by current. So finally we can write dimension of force MLT minus 2, dimension of area L square by dimension of current in A square, and dimension of length here L. So finally we will have ML square T minus 2 A minus 2. So dimension of L is written as ML square T minus 2 A minus 2. This is the dimension of L. Similarly, second point. So self-inductance of a loop depends on self-inductance of a loop depends on its geometrical shape and size, as well as depends on geometrical shape and size, as well as the medium, in which loop has been kept. So this is the main point related to the self-inductance. So it depends on the geometrical shape and size, as well as the medium in which the loop has been kept. Now, third point we can say calculation of self-inductance. Calculation of self-inductance. So for calculation, we can write L is equal to your phi by I. So this is the formula which we have to use for calculation of self-inductance. So what we will take, we will assume a current in the loop, and then we will try to find what is the self flux associated with that loop. So ratio of the self flux with the current in the loop is always a constant, and that constant gives us the coefficient of self-inductance or value of L. So see one or two examples. On the basis of that, we can get the self-inductance value for different type of loops. So see, now first is the self-inductance of circular loop of a small radius capital R having n number of turns. Now we would like to find self-inductance of a circular loop of a small radius R having number of turns here n, like this. This is the circular loop, and in this circular loop, let n is the number of turn and R is radius. So what we will do, let I is the current in the loop. If I is the current in the loop, so what we will do, we will try to find self flux through that loop. So since radius of loop is very small, so we can take uniform magnetic field inside the loop, and the magnitude of field and the magnitude of magnetic field is the same as on its center. So the self flux phi is equal to your, the first is the area. Each loop have area your pi r square, and total number of turns are n. The total number of turns if n, so total area will be your pi r square into n. And the magnetic field at the center due to each turn, mu naught by 4 pi 2 pi I by r. This is the magnetic field at the center, and then if n is the number of turns, the total magnetic field will be your multiplied by n. So finally self flux written as your phi, which is given as, now we can simplify 2 pi we can cancel, so mu naught and here then by 2 pi r square n square by r into I. So mu naught by 2 pi r square n square I by r. So L is your phi by I, flux by current ratio, 1r cancel, phi by I, it will become your mu naught pi r n square by 2. This is the value of self-inductance. The self-inductance in the loop L is given as mu naught into pi r n square by 2. From here it is clear the self-inductance is dependent on the radius of the loop as well as the number of turns in the loop. If inside a loop, suppose inside a loop if we are keeping a ferromagnetic material or suppose a cylinder of radius r made from ferromagnetic material. So rather vacuum inside, we are having a medium which can have magnetic permeability at mu r. So the mu naught value will change. Then we have to write mu naught into mu r, where mu r is the relative magnetic permeability of that ferromagnetic material. So we can say L value depends on geometrical shape and size as well as the medium in which the loop has been kept. Similarly, now see another case. Now see the second one, self-inductance of long solenoid or inductor. Solenoid we can say as inductor also. Self-inductance of a long solenoid or inductor. So this is our solenoid. And here R is the radius of solenoid, L is the length of solenoid, and total N is the number of turns. So let R is the radius of solenoid and L is the length of solenoid, and condition is that R is very, very small as compared to length. If N is the number of turns in the solenoid, then small n is written as capital N by L, where small n is number of turns per unit length. So these are the basic information related to the solenoid. Now we would like to find the self-inductance. Method is same. Self-inductance L is nothing, self-flux by current. It is the ratio of self-flux by self-current. Let I is the current in the solenoid. Current in the solenoid. So due to this current, due to this current, magnetic field inside the solenoid is given as magnetic field inside the solenoid is given as B is equal to mu naught Ni. So cell flux. Phi is written as B in a magnetic field into area of solenoid. Area of solenoid means each turn have radius r. So area of each turn written as pi r square, and total number of turns is capital N. So this we can write here. So phi further written as mu naught, capital N we can write, or Ni pi r square into L into N by L. N by L is nothing, that is same, that's this. So this further written as phi is equal to mu naught N square, and pi r square L become your volume, V into I. So self inductance L is equal to your phi by I. So this is your mu naught N square V. This is the self inductance of a solenoid, where V is volume of solenoid. V is the volume of solenoid. So in this manner, we can calculate the self-inductance of a different circuit or closed loop.